Hi, nice to be here again. Do you think that you're overweighted? Do you want to lose weight? Do you want to make your weight is equal to 0? No worries, please. You don't have to go to gym and work it out. You don't have to be in diet so that you can just lose the weight. You don't have to think much. I'm going to give you some solutions. But this time, I have got physics and I'm going to make a treatment in terms of physics. So what weight measures is just m into g. So weight is a measure of mass in gravitational acceleration. So that's m times g, where g is a gravitational acceleration. So I would be having an option to decrease the value of g, that is a gravitational acceleration, so that I can just reduce your weight. You don't have to go to g and do it m into j. So I'm going to decrease the g. So I'm going to tell you how to decrease g. And how, where exactly you have to go to make it 0 or decrease g. I'm going to tell you this. Now you have mass m. So I'm going to take you as an example here. This is Earth of radius r. Mass of the Earth is concentrated at the center, that is capital M is the mass of the Earth. And you are on the surface and you are in a difficult condition because you're overweighted. This is what your problem you have, for example. So I'm telling you that you are here with the mass m on the Earth's surface and you're overweighted. And how do I measure your weight? It's just m into g. So that's what gravitational force acting on you. There is nothing but weight. You think that you're overweighted, however. So now m is a mass of you or here on Earth's surface. Capital M is a mass of the body which is concentrated at the center. I just assume that Earth is clearly spherical of the constant radius r. For this time, m is a mass of the Earth which is concentrated at the exact center. And you are here on the surface. R is the radius of the Earth. Now I'm going to give you the expression for gravitational acceleration. And know that is just 9.8 meters per second square. Everyone uses the same when we solve the problem. So the g is 9.8. If I just drop a body from a certain height, for that case g substitutes 9.8. If I just throw one body from the top of the building, g should be taken as 9.8 meters per second square. It's a constant value. So I'm going to tell you now how exactly it is constant. Why exactly it is constant. That's what I'm going to do it now. Now for body is on the Earth's surface, it is to be taken constant. Which one? Gravitational acceleration. Now I just know that if the body is on the Earth's surface, there will be a gravitational force. There is nothing but weight. But what Newton told is there will be always a gravitational force of attraction between the body, that is u, and the mass of Earth, and that is mass. That gravitational force of attraction is given by F is equal to g, capital M, small m, by r square. This is what we know universal of gravitation says, and given by Newton. This is equation number 1. This is just gravitational force of attraction between you and Earth. At the same time, the same person Newton gave another law. It is called Newton's second law. That is just weight. Whatever the gravitational force acting on you is just nothing but the weight. That's what the problem you have, overweighted. So that is F is equal to m into g. The same person Newton gave in his Newton's second law. You know that. It is just mass times acceleration. Now acceleration is nothing but gravitational acceleration. So left hand side I've got gravitational force of attraction. For both the cases, the right hand side should be same. I'm going to equate the right hand side. So this time I'm going to do it here. Capital G, capital M, small m dividing by r squared. Remember, I'm sorry for this. This is just capital R squared. It's the radius of the Earth. And here it should be the same. Is equal to m into g. I lose my m, I lose u, because mass of u are not going to be counted any hurry because it's going to cancel it. So that implies g is equal to capital G, capital M by r squared. That means on the Earth's surface, gravitational acceleration is a constant. Acceleration due to gravity is a constant. How can I say that? Because g is a constant. There's a gravitational constant, which is again a constant term. Capital M is a mass of the Earth, will never change for the time being. And capital R is just a radius of the Earth, which is again a constant. So all the terms in the right hand side is constant, right and left hand side should be constant. So I can say, if I know the mass of the earth, radius of the earth, g is of this root, you know the value, constant value. If I substitute all the values here, I would get g is around 9.8 meter per second square. That's when all the problems we solve for the earth's surface, g should be taken as 9.8 meter per second square. Now I told you I am going to make g vary. How do I do? I'm going to tell you. I'm going to take you to the different spots so that if I vary the value of g, so that weight when I measure will be changing, right? That's what I'm going to do it for you. So g is just constant 9.8 meter per second square on the earth's surface. That means if I drop two different bodies of different masses, maybe one side you have an elephant, another side you have an ant. So if I just drop from a certain height, same height, at the same time, you may think that, okay, ant is very small and it is very light, it will take a lot of time to reach the earth's surface, but elephant is really heavy and it will take less time and it will reach first. But it is not the true thing, because gravitational acceleration or acceleration due to gravity is same for both of masses, because this guy is independent of small m, that is mass of the body. So it doesn't matter what is a mass, both the bodies will reach earth at the same rate, no matter, because g is a constant. Now if I can change the g, I can change the weight measure, because gravitational force acting on you may be getting changed. So how would I do it though? Now I'm going to take you into the certain height. I'm just making you to be above the earth's surface, maybe to the certain height h. This is going to take you up from the certain height and height h. Now I'm going to measure the gravitational acceleration at this point. If g changes, I could make w changes. That is, just weight can be changed. How would I do it? Now, if I just raise you up for the height h, what will happen is this g changes. I think so. That's why I'm just writing g dash. I've think if g dash is exactly g m by r squared, I can say that there is no variation of gravitational acceleration. But this time I just think that g changes if I just take you to the certain height h. That is equal to g capital M by r plus h whole square. This is just expression for the gravitational acceleration for the certain height h, where I'm going to raise you up. I'm going to take the ratio here, g dash by g. This is just g dash expression dividing by g. That is equal to gm cancels, and it is just r by r plus h whole square. If I divide by r on both sides, not both sides, in denominator and numerator, 1r cancels, so g dash is equal to g, that is 1 by 1 plus h by r to the power 2. And g dash is equal to g into 1 minus 1 plus h by r to the power minus 2. Remember, this is just a variable here, h by r, because h can be varied. R is just the radius of the earth. Now if I use the binomial expansion, what I could do is, I can just expand 1 plus x to the power n is 1 minus nx plus nx squared by 2 minus nx cubed by 3 factorial, so on. For the timing, I'm going to take a very special case. That special case is the height where I'm going to raise you up is not so high. When I compare with the radius of the earth, which is very, very great compared to the height, this will happen. Height is going to be very, very small compared to radius. So radius of the earth is around 6,400 kilometers. A height is not so much, it may be around 50 kilometers, 100 kilometers. Compared to the radius, height is not so high. So if this is a case, what I could do is h by r whole square. So second order, third order, fourth order, and higher order polynomial in the binomial expansion, if I do it for this, will not exist. Then it will, you can ignore it completely. So after getting binomial expansion, I've been just taking a binomial expansion. So g dash is equal to g into 1 minus 2h by r. I have to ignore the higher order terms because this is a case. If h is very lesser than r, h by r is very, very less. And h by r whole square could be ignored completely, and even cube, 4, etc., etc. So only one term I have got is this 1 minus 2h by r. This is just by binomial expansion. This is a gravitational acceleration at the height h, raised from the surface of the body. Now question comes whether it is increased, whether it is decreased. I told you I'm just going to reduce your weight. I didn't tell you simply. I'm going to reduce your weight because if I measure your weight, maybe after, if I just take you to 100 kilometers above the earth's surface of the earth, if I measure your weight, it may not be the weight whatever I measure on the earth's surface. It will be less so that you will be happy. You don't have to go for an diet. Oh, okay, I'm all happy. I just got light weight. You will be happy for the time. Because G dash, that is gravitational acceleration, at a certain height from the surface of the earth is not 9.8 meters per second square. It is less than that because I've got negative sign times h. That is, if you go for higher, greater and greater heights, G, that is gravitational acceleration, decreases. So if I just go above and above and above the earth's surface, G value keeps decreasing. So if you really want to lose your weight, you have to go to the certain height and measure the weight, because weight is just multiplication of mass and gravitational acceleration. So G you can decrease by taking yourself to the certain height, and ultimately W, that is weight, could be decreased. So you don't have to worry much about losing your weight. Another way I will tell you to lose your weight. I can make your weight is completely zero. That's my another case. I will do it later. Now, what I'm going to do is, instead of just going up or going above the surface of the earth, I'm going to make you to be inside the earth's surface. Here you are. This is just the radius of the earth, right? And you are here, and you are going to be inside the surface of the earth. I'm just going to take in and put it inside. And maybe for the depth D, that's what I'm going to do. So here you are at a depth D from the surface of the earth, and this is the mass of you. And capital M is just mass of the earth, and R is the radius of the earth, and this is just R minus D, that is the radius of the spherical shell or sphere where you are situated on the surface of the sphere. That's what I have now. Again, the same thing comes. Suppose rho is the density of the earth. What I have is rho is equal to mass by volume. Mass by volume of the earth is just 4 by 3 pi r cube. I want to write for mass, m is 4 by 3 pi r cube times density. On the earth's surface, G value is equal to capital G by r squared times mass of the earth. That is written here, that is 4 by 3 pi r cube times rho. So you lose your r cube and r squared, so you will get back with the r. So 4 by 3 pi rho g times r is just gravitational acceleration on the earth's surface. So same expression I've written in terms of density. That's what I've done by taking density as mass by volume. Mass of the earth, volume of the earth. That's what I've done. Now, if I just get inside the earth for the depth d, so the gravitational acceleration at that point with the depth d is just 4 by 3 pi rho g times r minus d. This is the distance, r minus d. I'm going to take the ratio again, g dash by g, that's equal to 4 by 3 cancel, pi cancel, rho cancel, g cancel. So I left with r minus d by r. That is just 1 minus d by r. So that implies g dash, there is a gravitational acceleration at the point here with the depth d is just g, not only g, that is not only 9.8 as like last time, not only it is 9.8, it was 9.8 times something less than that. Yeah, absolutely. Here also g times 1 minus d by r. Again the question comes, if I go inside, if I make it to be inside the Earth for the depth d, whether you lose your weight or gain your weight, this equation tells you that you're going to lose your weight because g dash, that is a gravitational acceleration at a certain point inside the Earth, decreases because you've got minus sign here. So there is a depth decreases as you go inside the Earth. So this negative sign says that if you go inside the Earth to the certain depth, g value completely decreases. And so finally what I just inferred is on the Earth's surface, g value is maximum, that is 9.8 meters per second square. If I go up, g value keeps decreasing. I got a good evidence here, it's a minus sign. And if you go inside the Earth also, g value decreases. So on the both sides, above and below, gravitational acceleration value decreases. On the Earth's surface, it becomes a maximum value, that is just about 9.8 meters per second square. So another thing is I want you to get zero weight. If you want to have that, I could tell you that's one of the best things here. This time, if d is equal to r, if these two factors are sine, this is 1 by 1, 1 minus 1 is equal to 0, so g dash is equal to g times 1 minus 1 is equal to 0. So gravitational acceleration is 0 for this case, then I can say that the weight is just m into times j, gravitational acceleration is 0, so mass times gravitational acceleration is 0. So weight is completely equal to 0. So how could I make it now? This means d is equal to r. So if I just increase my d, and if I just take it r, that means I'm going to take u into the center of Earth, and I'm going to measure the weight. And the weight will be equal to 0 because at the center of the Earth, gravitational acceleration becomes 0. Weight is just multiple of mass in the gravitational acceleration. G becomes 0, weight has to be equal to 0. So I just made you a weight 0. So thanks for watching this video. Keep you in touch next time.